This video is going to show you how to control NeoPixels using the Arduino Nano RP2040 Connect. This is going to use the wireless features of the Arduino, allowing for NeoPixels over Wi-Fi. It's also going to explain about voltage shift circuit options and the importance of prototyping a circuit before creating your final design. I nearly went straight from the idea to PCB, skipping the prototyping stage, but that would have been a costly mistake, which I'll explain later. I've split this video into chapters, so if you want to skip straight to the relevant part, then you can do so. Here are the approximate timings, but you can also skip using the video timeline or links in the description. I'll start with an introduction to NeoPixels and the idea behind the project, including explaining about the wireless features of the Arduino Nano RP2040. I'll be covering what the Arduino Nano RP2040 is, and which is Arduino's implementation based around the Raspberry Pi RP2040 microcontroller, as used in the Raspberry Pi Pico. I'll explain what this project will eventually achieve. This is only the prototyping stage. Future videos will explain more. Next, I'll explain about the electronics and the prototyping stage. I'll be explaining the reason for prototyping and 2 reasons why this nearly didn't work. I'll talk about the voltage level shifter, the one I normally use, which didn't work as well as the new improved version. Then look at the software side for the Arduino Nano RP2040 and how to set up the appropriate libraries and program the Arduino. Finally, I'll give a quick demonstration of the project so far and my future plans, including installing this project in my garden. Firstly, what are NeoPixels? Or perhaps more appropriately, PixelStrips. These are addressable RGB LEDs. Each LED can be individually addressed and set to any colour you would like. The addressable LEDs consist of an RGB LED, that is 3 different coloured LEDs in a single package, with an accompanying controller, typically a WS2811 or a WS2812. These are often stacked, so when you look at the NeoPixels, you just see the LED and the integrated circuit is hidden underneath. The individual controllers can be stringed together with the data out pin connecting to the data in pin of the next IC. Effectively, you only need a single pin from the controller, which connects to the first LED controller. NeoPixels is the name that Adafruit use for their brand of addressable LEDs. I do often use Adafruit branded NeoPixels, particularly for their small strips or NeoPixel rings, but I won't be in this case as I'll be using some branded PixelStrips that I already had. There is more information about PixelStrips on my website. With these PixelStrips you can create mood lighting or light displays, which are not achievable with most of the commercial shop-bought LED strips. For this project I'm looking to create a wireless controller for my PixelStrips. This will allow control of the LEDs using a simple web interface and a graphical user interface running on a computer. In future, I may look at other ways of controlling these, perhaps with Google Home or Amazon Alexa. The Arduino Nano RP2040 Connect is Arduino's response to the Raspberry Pi Pico microcontroller. I've gone into more details on this on an earlier video. See the link in the description if you want to find out more about that. As a quick summary, it's based around the RP2040 microcontroller, which was designed by Raspberry Pi specifically for the Raspberry Pi Pico. It's not a full computer in that it does not run an operating system, but it allows for code to run directly on the microcontroller. The Raspberry Pi Pico is very cheap, but it is also very basic. For example, there is no wireless network connectivity, which is where the Arduino Nano RP2040 comes in. It includes a built-in ESP32 wireless module, which makes it easy to incorporate wireless connectivity into your project. The Arduino is also smaller than the Raspberry Pi Pico. But all these features come at a price, as the Arduino is significantly more expensive than the Pico. As the saying goes, you get what you pay for. And if you want the additional functionality, then the Arduino provides that. Unlike the traditional Arduino, which runs at 5 volts, the Arduino Nano series, including the RP2040, all run at 3.3 volts. This is going to be important later when we come to the design. If cost is your main consideration, then the Raspberry Pi Zero comes in as a cheaper wireless alternative, but it's not necessarily the best solution. I've used the Pi Zero for my existing PixelStrip setup on my drive. I'll include a link in the description if you prefer to use a Raspberry Pi Zero. But arguably, a microcontroller is better for controlling the PixelStrips. They are better at handling the timing needed for the WS2812 ICs, and without having an operating system, they can be powered on and off quickly and without risk of corrupting the SD card. They can therefore be more reliable, and this is the reason I decided to go with the Arduino. The design for this is straightforward. The PixelStrip needs to be powered directly from a 5-volt supply. It does need a powerful power supply, which depends upon the number of NeoPixels that will be powered from it. For full brightness white, you need to allow for around 60 milliamps per pixel. With 100 LEDs, which is a reasonable number, then that needs a minimum of a 5-volt 6-amp power supply. The Arduino will be responsible for generating the signal for the PixelStrip. Remember I said that the Arduino Nano RP2040 Connect runs at 3.3 volts. If you're using a traditional Arduino, which runs at 5 volts, then you can connect that direct to the PixelStrip data input, which is something I've done before. When you have a device that only outputs 3.3 volts, then you need to step that up to 5 volts to guarantee that they will work correctly. It may be you could skip this and just connect 3.3 volts to the PixelStrip and it will work. However, you should be aware that this is outside the design capability. You may also find that it works in the lab, but then when you go out to deploy it outside, then the signal quality is degraded and it doesn't work. This is something I found in practice when I installed these in my front garden, as I originally planned to control the PixelStrip from the Raspberry Pi at the front of my house. But due to the distance, I had to instead mount the Raspberry Pi in a waterproof box near to the actual strips. I recommend trying to stick with the design specifications, especially when intended for use outdoors. I am therefore using a voltage level shifter to increase the signal voltage to 5 volts. I originally intended to use a simple MOSFET inverting amplifier, as I've used on my Raspberry Pi, but fortunately I tried prototyping this first and found that it didn't work. After coming up with a design, it's usually a good idea to prototype it, say on a breadboard. This allows you to test the solution before committing to a permanent design. In my case, I hope to put this on a PCB. I was tempted to skip this stage of the project. After all, I've used PixelStrips with an Arduino before, and I've also used them with a 3.3 volt Raspberry Pi with a MOSFET buffer, so I was confident that this would work. However, the Arduino is very different to the one I've used before, and it's the first time I've used this buffer circuit with the Arduino, so I decided to test on a breadboard first. I'm glad I did. It turns out that there's two problems with my first design. I'm not sure the reason for one of the problems, but fortunately I ironed these out at this stage prior to designing the PCB. The first is the choice of port. At this point, I don't know what was wrong with my initial design. I originally tried to use D2, which stands for Digital Port 2. This was just an arbitrary decision based on it being the first suitable digital port. Digital ports 0 and 1 are used by the UART. It's also known by the designation GPIO 25, which is based on the RP2040 numbering. The problem with this is that for some reason it interfered with the Wi-Fi communications. I don't know why this is the case. I've looked through the Arduino technical reference and it doesn't mention any conflict. When I tried to use the Wi-Fi connection and enabled the PixelStrip output on port D2, then I ended up with a corrupted Wi-Fi signal. I instead moved this connection to D3, which is GPIO 15, which worked fine. If anyone is aware of possible conflicts between inputs and the Wi-Fi module, please leave details in the comments, as that would be useful to know for future. The next problem is a voltage shifter. The circuit I normally use to run NeoPixels from a Raspberry Pi is a single-stage MOSFET switch, which provides an inverted signal. This isn't a problem when using a Raspberry Pi, as the library used on the Raspberry Pi includes an invert option, which inverts the signal from the Raspberry Pi GPIO port. The Arduino traditionally is designed for 5 volts, and as that doesn't need to invert the signal, then it doesn't have that option. I could take the library and modify it, but I'd rather stick with the standard library. I fixed this by using a non-inverting buffer, which I'll explain next. Basically, I was glad that I did prototype this on the breadboard first, as it would otherwise have resulted in wasted PCBs, or at least it would have been difficult to resolve afterwards. I'm going to go into a bit more detail on the level shifter I didn't use. This is to explain why it didn't work, but it also gives insight into one possible solution. The one I actually used works differently, which I'll explain. I think it may be worth creating a video just on level shifters in future, as there are lots of other ways this could be achieved, each with their own pros and cons. First, I'm going to show my normal go-to level shifter. This is what I normally use when I want to control NeoPixels from a Raspberry Pi. It's very simple, needing only a single N-channel MOSFET and 2 resistors, and it's easy to understand how it works. Its one failure, at least in terms of this project, is that it's inverting. As I said previously, that's not a problem when you can invert the signal in the code, but the standard Arduino libraries don't support that. This animation is going to show the current flow. As I'm using a MOSFET, this is more about voltage, or more specifically charge. There will still be some current flow, so the diagram is correct, but the current into the input of the MOSFET is going to be very small. With the input at 0 volts, the MOSFET is in the off position, and no current can flow from the drain to the source. In this case, resistor RL is a pull-up resistor, and it connects the output to the 5 volt supply rail. A current can flow through RL to the output, giving a 5 volt output. The output may be slightly less than 5 volts, depending upon the impedance of what it's driving, but in this case it's a high impedance input to the WS2811 or 2812, which will use only a small current. Now, when the input to the buffer goes high, a current flows through RB, which places a charge on the gate of the MOSFET. Initially, this current can be quite high, which is why RB is included to limit the current being drawn into the input. Once the MOSFET has sufficient charge on the gate, it turns on and effectively acts as a short circuit from the drain to the source. This pulls the output low and a current can flow through RL to ground. The output is now at 0 volts. This is the theory. We can look at what it looks like in practice by using an oscilloscope. This is the output showing the trace on an oscilloscope. You may need to view this in HD to be able to see it, or you can view a static image on my website. See the description for details. This looks a bit confusing at first, but let me explain. I'll be showing a logic analyzer output later in the video, which will show this a bit clearer. But the oscilloscope shows the difference in voltage, which is what I'm wanting to show here, as well as the inverted signal. The input is the signal in yellow, and the output is the signal in green. The first thing to note is that the green signal is taller, indicating a high voltage. In this case, just under 5 volts, whereas the yellow signal is around 3.3 volts. There are some spikes that exceed those, but we can ignore that. This just shows that the voltage is increasing. In an ideal world, these signals would change from one voltage to another instantaneously. You'll see that's not the case, but this is within the tolerance. Looking at the top of the yellow trace, you'll see that there are signals with different width. Some are narrow, looking like spikes, whereas others have a flatter top to the signal. You can ignore the mini spikes. Next, you'll notice that the green line does the opposite, going down instead of up. So where there is a narrow spike at the top of the signal, there is a narrow spike at the bottom of the green signal. The same for there's a wide trace at the top of the yellow signal, there's a wider spike at the bottom of the green. I'll show these signals in a logic analyzer, but first, how can we fix this inversion? The first thing we can try is to invert it again. If the MOSFET amplifier inverts it once, we can add another stage and invert it back again. This is what's shown in this diagram. The second stage does not need to amplify the signal, but just inverts it back to the original. This is the trace on the logic analyzer, showing 3 signals. Again, if you have problems seeing this, you may want to look at my website where you can view a static image of this. The logic analyzer just looks at logic levels, so it's cleaned up all the noise that you saw on the oscilloscope. It doesn't, however, show the voltage. Instead, it assumes that all three signals are at the same voltage. The bottom signal, which is the brown, is the original signal from the Arduino. The next line up, which is in red, shows the output after the first stage, which is the same as the inverting amplifier that we saw on the oscilloscope. As you can see, when the input goes high, the output goes low, and vice versa. You'll also notice a very small time shift. The third trace, which is in orange, shows the output from the second stage. As you can see, this follows the original input, so it's no longer inverted, but it is shifted along a little bit further, so there is some delay between the input and the output, which is the switching speed of the two MOSFETs. And it can also be affected by the size of the base resistor. This delay is not an issue with how this is being used here, because the NeoPixels still get the same signal just a few nanoseconds later, but it is something you may need to be aware of with certain other circuits. I instead use this circuit, which is simpler in terms of the number of components, but it's not quite so intuitive to understand. This is only two components, a MOSFET and a pull-up resistor. As before, with the MOSFET switched off, then the pull-up resistor sets the output high, and when the MOSFET is on, then the output goes low. The way this works is based around the voltage difference between the gate, which is pin 1, and the source, which is pin 2, which is what connects to the Arduino. If the input to the circuit is low, so that's 0 volts coming from the Arduino, then the voltage difference between the gate and the source is 3.3 volts, which turns the MOSFET on. Remember that this causes the output to go low. If the input to the circuit is high, so that's 3.3 volts at the source, then the gate and source are both at 3.3 volts, so the MOSFET switches off and the output is pulled high by the pull-up resistor. This uses a similar principle to the Adafruit bidirectional voltage shifter, which is another alternative we could have used. I've just explained it in one direction. It uses a similar principle in the other direction, but this time you need to consider the drain to source voltage to determine if it's switched on or not. I don't need this to be bidirectional, but it works just as well in just the one direction, and this is the method I've used for this circuit. There are other ways to change the voltage. One example is the 74HCT-XX series of logic integrated circuits. These have a CMOS 5V output, but they work on both TTL and CMOS inputs, so they will accept a 3.3 volt signal as a high. One example would be to use the 74HCT08, which is a collection of AND gates. If you connect the two inputs to the AND gate together, then that would just act as a simple level shifter. As I said before, I decided on the single MOSFET non-inverting buffer. It uses minimal components and it works well in this situation. I used a 1 kilo ohm resistor for the pull-up resistor to keep the current through this fairly low. Here's the circuit shown on the breadboard. As you can see, there are only 2 LEDs on this board, which is just for demonstration purposes. The actual PixelStrips are the same, but they just have more LEDs chained together, with the data out from one going to the data in for the next LED. The example for controlling NeoPixels here uses a web server with a simple 3-button input representing red, green and blue. Depending upon which of the buttons is turned on determines the colours of all the LEDs on the strip. This is only a very basic operation compared to what can be achieved, but it's a starting point. It's based on the Wi-Fi web server example that is provided by Arduino. I then combined this with the Adafruit NeoPixel library, which has been updated to support the Arduino Nano RP2040 Connect. You can install the library through the Arduino IDE. I've already explained in an earlier video about the Arduino Nano RP2040 and how you can use that with the Arduino IDE, So if you've not set up your Arduino yet, then you might want to go and check out that video and then come back to this. As I mentioned previously, there's a link in the description to that earlier video. The only additional step compared to that video is that I've gone into the library manager and searched for NeoPixel. Then installed the library called Adafruit NeoPixel. Note, it's not the one called Adafruit DMA NeoPixel or any of the other results. Just install the latest version of the one called Adafruit NeoPixel, which in my case is version 1.8.3. This is the code which I've used, and it's mainly based around the RGB web server code that I used in my earlier video, and is the example provided by Arduino. I've placed the Wi-Fi authentication information into a separate file called Arduino_secrets.h. Next, I've defined which pins are used and the LED count. Note that the pin number is the GPIO pin number rather than the physical pin or the digital pin reference number. The web server is then defined along with the NeoPixel strip. You may need to change some of these parameters depending upon what kind of NeoPixels, for instance, you're using. For example, this uses GRB, where the data is sent as green, red and then blue, whereas some other pixels are wired differently and need that in a different order. The setup includes the pin mode for the standard built-in LED as well. So this can be useful for debugging. So if you have a problem with the NeoPixels, it shows you if the web server is working correctly and setting the colours correctly, and indicates whether you need to look at the NeoPixels or the web server code. I've given the Wi-Fi of the Arduino a static IP address, which makes it easy to connect to because you know what that address is. Then there's some Wi-Fi code followed by setting up the NeoPixels. You'll see that strip.begin is called, but that only needs to be called once, whereas the strip.show needs to be called every time that the NeoPixels change colour. Most of the code in the loop function is from the demonstration program. You'll see that I've stored the status of the colour R, G and B into variables when they're either turned on or off. Then I can use those in setPixels to set the specified sequence. The only sequence currently supported in this example code is all on, which turns on all the LEDs based on the colour values that I mentioned earlier for the R, G and B values. The rest of the code is to output the HTML code for the web page, and there's some print statements for the status of the Wi-Fi connection so you can see when they've connected correctly. Now here, as you can see, as you click on each of the buttons on the web page, you can see that the colour of the NeoPixels changes as well. This is just showing the two NeoPixels that I've added to the breadboard, but this would be the same if it was connected to a whole string of LEDs as well. I plan to develop this further in future. This will include creating a custom PCB to allow the Arduino to be mounted onto it with the voltage shifter on the PCB board. I then intend to design a case, or perhaps fit it in a standard case. This will then allow it to be mounted outdoors, connected to some waterproof PixelStrips. I also want to add more colour sequences, similar to how I've done this for the Raspberry Pi, allowing different sequences of flashing lights, chasers and colour changing sequences. And finally, I hope to provide both an updated web interface and integration with my current graphical user interface, or perhaps a new graphical user interface. I'm not sure which yet. This will likely be a client-server architecture which integrates with the web interface. If you're interested in any of the future development, please subscribe to my channel and click the notification icon to get notified of new updates. If you think this has been useful, please give it a thumbs up. If you want to help support the development of this, you can even give it a super thanks using the button below this video. I hope you enjoyed this. I look forward to seeing you on a future video.